A uniform circular disk of mass 50 kg and radius 0.4 meters is rotating about its own axis, which is vertical. So here, if we take the disk, so this is the disk. Let's imagine that we are looking from above. So this would be the top view, and the axis is coming out of the board. And let's say the disk is rotating in the counterclockwise sense with an angular velocity of 10 radian per second. Now the problem says that two identical rings, each having mass 6.25 kg and radius 0.2 meters, they're placed symmetrically on the disk in such a way that the rings are touching one another. If you ponder a little, you will notice that this can only happen at the center of the disk. So if this is our disk, the rings must be placed something like this. So they're touching exactly at the center of the disk. Now, if we take our system to be disk plus the two circular rings about the axis, okay, so this is our axis. About the axis, there is no external torque. Because there is no external torque, the initial angular momentum of the system must be equal to the final angular momentum of the system. Now, there were no rings initially, only the disk was rotating about the fixed axis. So the angular momentum of the disk is I omega. So we can say I is m r square by 2 into initial omega. So let's say omega. Now finally, once you place these rings, the problem also mentions that there is sufficient friction that these two rings do not slip relative to the disk, they stay at rest. So they are in the position shown and they are rotating with the disk. So the moment of inertia would include the moment of inertia of the rings as well. But the rings are not getting rotated about an axis passing through their center of mass. So we are supposed to use the parallel axis theorem when we get their moment of inertia contribution. So for the disk, there is no change. We still have mr square by 2. Now if I say that mass of each ring is small m and the radius is r, so we can write, had the ring been rotated about an axis passing through center of mass, then it would have been mr square. But here we have to use parallel axis theorem, so I have to multiply by that md square. In this case, d is, we'll have to add mr square. And again, we have two identical rings, so this should be multiplied by 2, and then this gets added to the overall moment of inertia. And then we have this final angular velocity. Now here I think if you substitute the values, mass of the disk is 50, radius is 0.4 square over 2, and initial omega is 10. So this is 50 into 0.4 square by 2, plus I think I can take this as 4 mr square, so, right? 4 m is 6.25 multiplied by r square is 0.2 square, and this entire thing will be multiplied with final omega. Now if I look on the left hand side, this is 0.16. How much is this? I think 0.16. So this is 40. We can say this is 40, and on the right hand side, if this is 40, and then the first term should be 4. 4 plus I think 6.25 times 4 would be 25, and then we have 0.2 square. So I think that would be 0.04 into 25, so that should be into final. So I think this is 5 into omega. So final omega should be 8 radians per second.